All right, guys, this video is going to be quick. You're going to like it, but there's a few homework problems associated with it. This is a super duper typical AP question, and I've seen it show up on both the multiple choice and on the free response question of the test. So it's quick to find. Let's talk about how you show the work. So right now, I know that I have a piecewise function where the left-hand end is some sort of cubic function and the right-hand end is some sort of linear function. So I want to make the two pieces connect at x equals 1. So if I go about my regular deal, I'm going to say, well, the left-hand piece ends with 1 comma 3 when I plug in. The right-hand piece starts with open circle 1 comma. Now if you plug in 1 for x, you just get a plus 5. So do you see what has to happen? Do you see that for the function to be continuous, I need to make the open circle and the closed circle come together? They need to connect. And if that's going to happen, then the y coordinates of the 2 points have to be the same. So that would just mean that make the y coordinate of the second piece equal to the y coordinate of the first piece. So not so bad, right? So you're also looking at it if you wanted to be a little more formal with your approach. If you were on the free response part of the test, you could say, well, the limit as x approaches 1 from the left-hand side is equal to 3. The limit as x approaches 1 from the right-hand side is equal to a plus 5. And the idea is that f of x is continuous at x equals 1 if when, I'm going to erase that because that's not exactly where I was writing it, if the limit as x goes to 1 from the left, which equals 3, equals the limit as x goes to 1 from the right of f of x. So that's going to make the overall limit exist, and you want that to equal f of 1 as well, because you want the limit to equal the function value. So I just said a whole bunch of stuff, but anyway, it's this formal kind of reasoning that gives you license to get to the point of saying that this 3 must equal that a plus 5. But you've already done that, and we already know that a equals negative 2. Now the next thing that we're going to get into is a little different. It's about the intermediate value theorem, but let me sort of wrap up this discussion of continuous functions with just some tidbits. So I am considering functions that I already know to be everywhere continuous. So if I look at y equals x squared, that's a polynomial function that's everywhere continuous. Y equals the absolute value of x, you know, is a right side up V-shaped function that it's everywhere continuous. And y equals sine of x, you know, is a wave, and y equals cosine x is also a wave. You know that they are everywhere continuous because none of the 4 functions I've introduced have holes or poles or jumps anywhere. So anytime you add 2 functions that are continuous, subtract 2 functions that are continuous, multiply 2 functions that are continuous, then you're going to wind up with a new continuous function. Why have I not said divided 2 functions that are continuous? Well, because think about it. If you said, well, what about y equals sine x over cosine x? Now I'm dividing 2 continuous functions. We've already addressed that. I get y equals tangent x, and you know tangent x has a whole bunch of discontinuities at the vertical asymptotes. So that's why I'm specifically leaving out dividing continuous functions. You can multiply any function by a constant, and it's still going to turn out continuous. Also, any composition of continuous functions. So remember, a composition is f of g of x. So if you nest a continuous function inside another continuous function, the resulting function is also continuous. So that's a wrap-up of continuity. Now we're going to get into the intermediate value theorem, which applies to continuous functions. And so the idea is pretty simple, and we'll go into this more in the next video. But the idea is that if you have a continuous function f of x, and you know the value of f of a, which is a y value that goes with the x value a, and you know the value f of b, which is the y value that goes with x equals b, and you know the graph of f of x is continuous between that left x and that right x, then every y value in between f of a and f of b will be picked up by the graph. So if you look, I'm going to say, well, look, here's a y value and here's a y value. So pick any y value in between. Okay, I'll pick one right there. That's a y value that falls in between f of a and f of b. Well, there's a point on the graph that goes with that y value, at least one. So look, I just found a point on the graph, and I could call that point c comma f of c. And the c value will fall between a and b on the x-axis. That's what the intermediate value theorem is saying. Well, notice it might not just be one point on the graph. So I could say, well, look here. Look at this y value on the y-axis that falls between f of a and f of b. Well, I see that it is picked up on the graph here. Oh, sorry, here and here. So the intermediate value theorem says f of x will pick up that point in the graph at least once, but it might pick it up multiple times. But again, every point on the graph, so if I drop it, I drop down, there's an x value, there's an x value, and of course there's an x value. The x values of those points are always going to fall between the left and right given x values at a and b. So every single y value between f of a and f of b will be represented somewhere on the graph, and the corresponding x values will fall between a and b. So that's where we're headed. We won't do any problems with that yet. Let's go ahead and do a few more homework problems on continuity.